good. Well, on that note, I want to get started.
Okay, great.
Yeah. So just a couple of announcements. Where are you and what are you watching? So tonight we have Dr. Philip Mansfield on why and how galaxies die. And this is the East Bay Astronomical Society April General Meeting. And our host for tonight is Dave Rodriguez. Once again, Dave Rodriguez. I do have one or two announcements. Our next members only viewing night on the Chabot deck is scheduled for May 8th. So watch your email. We'll have a reminder go out on Night Sky Network. Obviously watch the weather as well. We've had really humid weather recently, and you know that the telescopes are not open once we get to, like 85% humidity, and that closes down Nelly, and the other telescopes close down at 90%. So, come on up if it's a nice night, and we'll hopefully see you then. The Telescope Makers Workshop is running every Friday night from 7 to 10. We do have a good set of students who are, working on projects that came back to life much quicker than we anticipated after being closed 2.5 years. In fact, we had somebody finish their mirror last night that he had started a couple of years ago, and then had to pause and then came back and finished it. We've had several families come back after having started their project like January of 2019, right? And then everything shut down. And then they come back, and the kids, of course, are 2 feet taller, and I barely recognize anybody. So anyway, it's been a lot of fun. Of course, all EAS members are welcome to drop in and say hello at the Telescope Makers Workshop. And of course, we have the regular Friday and Saturday night viewing through the Chabot Historical Instruments and through Nelly. So that's really all I got in the way of announcements. Dave, I'm going to leave it to you to introduce our speaker. And I ask that our all of our attendees have a little patience. I'm going to be displaying the slides tonight while Dr. Mansfield talks. We're just working around some technical difficulties that are forcing me to be attentive and more attentive than usual. So we will go from there and see how it works.
Thank you very much, Rich. So tonight it's my very great honor to introduce Dr. Phil Mansfield from the Kavli Institute for Particle Physics, fellow at Stanford University. There we go. Very good school. And I want to assure everybody that my spies at Stanford tell me that Phil's a very good speaker. I'm very much looking forward to this talk. We haven't had a good dark matter talk in a long time. His talk tonight is entitled How Galaxies Die, the Dark Matter Murder Mystery. No, the butler did not do it. I do want to say that I think that it's absolutely fascinating. If I remember correctly, dark matter comprises something like 75 or 80% of the total matter we see in the universe, and we don't know what it is. This is an incredible puzzle. Dr. Phil Mansfield, he got his PhD at University of Chicago, which from what I hear is a pretty good school. And he studies large-scale distribution of dark matter and the connection between dark matter and galaxies. And he's particularly interested in satellite galaxies, like those 2 galaxies we see orbiting the Andromeda Galaxy when we look at it through our telescope. So without any further ado, Dr. Phil Mansfield. Go ahead, Phil. Thank you very much for speaking to us.
And thank you for that great introduction. And thank all of you for showing up. I'm really excited to talk to you today. And I apologize again for sort of the technical glitches on my end. So what I'm going to talk about today is how galaxies die. And I'm going to start off in kind of a weird way for an astronomy talk. Next slide, please.
Okay, let's get there. There we go.
All right, I'm going to talk about this guy right here. So this guy is Immanuel Kant. He's one of sort of the most famous philosophers in the Western canon. He's responsible for some really, really cool ideas about metaphysics and ethics and all of this interesting stuff, albeit a little bit difficult to read. But he had a hobby that he did on the side, and he was basically a Revolutionary War era Bill Nye the Science Guy, who was really interested in trying to explain scientific ideas that he found interesting to the general public in a way that they could describe. Next slide, please. And so one of his big works was something called The Universal and Natural History of Heaven, which is essentially just him trying to summarize the current scientific thinking on where all the things in the night sky came from and what they were. And in cases where he ran into sort of the limits of scientific knowledge at the time, he would make an educated guess. And he was a really smart guy, and oftentimes his guesses were pretty good. Next slide. So this would be sort of the night sky as a, people at the time would understand it. And there's a lot of stuff here that's familiar. You can see there's all these stars. There's this giant band going from the bottom to the top of the screen. This is our own Milky Way. And sort of among here, there are planets. And Kant would go through these one by one, and he would talk about them. So for the stars, at this point, people already knew that stars were much like our sun, just only much further away. And for the Milky Way, people had figured out during the time of Galileo that the Milky Way was a collection of billions of stars, because if you take a telescope and you zoom in on that band of light, you start seeing that it's actually broken up into many, many stars. You can see just an innumerable number of them. When he talked about the planets, he even came up with a pretty reasonable theory for where they came from, that there was some sort of disk of primordial gas or matter that flattened out and then fragmented and then collapsed into planets. This is absolutely what happened. He didn't get it entirely right, but given what he had at the time, it was very remarkable that he got that. But as you read through this book, there's sort of one section in it which stands out from the others. And it was when Kant was talking about another object that is shown in this image. So next slide.
Galaxy.
And that's right here. So if you go out on a really dark night and you look up, just sort of off the axis of the Milky Way, you can see another blob that's distinct. It's pretty dim. If you stare at it dead on, it'll get caught in the blind spot in the center of your vision. But it's this little tiny faint oval. And the thing is that people had no idea what this was. So when Kant was describing the theories at the time, they weren't these physical ideas like they were for planets or for stars or for the Milky Way. They were sort of more metaphysical. One of the leading ideas was that this was literally a hole in the fabric of the universe that you could see, the fires of eternity and heaven through, this sort of stuff. Other people thought it was some totally unknown form of matter that had formed a disk or something like this. Kant's suggestion was that it was something closer to our own Milky Way. So our own Milky Way is probably shaped like a disk, he argued, and we don't need to introduce anything new if this is just another one of them. Next slide. And this is what ended up happening. So here's an image from the Hubble Space Telescope of sort of this little blob. And if you look at it, you can see all this rich structure. And if you were to zoom in even more, you could see that it is made up of many, many different stars. Although the debate about what these things were would rage on for centuries afterwards. Astronomers didn't really figure out what these were until after Einstein had even sort of come up with special relativity. It was in the early 1900s when people were able to work out exactly what this was. Next slide. But if Kant had been in the southern hemisphere, he would have seen even more sort of brilliant examples of these external objects that he was so interested in. So on the right-hand side of this screen, you can see these two white blobs next to the Milky Way. So in English, we refer to these as the Magellanic Clouds, but of course, almost every culture in the southern hemisphere has their own names and sort of stories and legends for these things for thousands of years. And these are also galaxies, but they're much closer to us. And somewhat ominously, these galaxies are about to die. So it's not going to happen, tomorrow or anything like this. Everything at these scales happens very, very slowly. So from the perspective of every human who's ever lived, these galaxies have been frozen in their place in the sky, essentially as long as we've been sentient beings. This is not true for the stars around us. As we orbit our galaxy, those stars and constellations are shifting and reforming into new configurations. But those galaxies are moving much more slowly across the sky. And this would happen even if we sped things up. So if we started to speed up time so that, ice ages are passing every second, that, old growth forests are flickering in and out, maybe then we would start to see them twist a little bit. But we'd have to go even further and faster before we could start to see them move. And if we sped up time to the point where, the sun is starting to die and, oxygen is getting reabsorbed into the rocks of the Earth, then we'd start to see them tumble towards the Milky Way. They'd start to shred apart and collide with it and be entirely obliterated. And this process of how a galaxy dies and ends its life is what this talk is about. And we're going to unpack that a little bit. Next slide. But to talk about what it means for a galaxy to die, we need to talk about what it means for it to be alive. So what do I mean when I say that they stop living in the first place? Next slide. So the way that I like to think about it is in terms of breathing. So human beings breathe in and out. We take in air and breathe out CO2 in order to sort of power our bodies, to allow us to grow and to do things. And galaxies are in a very similar situation. They have flows of gas that come into them and power the formation of stars that allow it to evolve into different forms over time. And they blow that gas out in a changed form later. And this whole process is very closely related to what we mean when we say that these things are alive. Next slide. So let's imagine that we were, a scientist who is interested in human breathing. There's a couple questions that we might ask to just get the basics of what's happening here. So we might ask something like, what types of gases are being breathed in and out when we do this? What is it that comes into our lungs and what goes out in the first place? We might ask why that allows us to live. What is it about that gas that allows us to keep on moving? And then we may also ask what even causes the breathing, what inside of our bodies allows this to happen. And, in the case of humans, it's air that comes in, CO2 that comes out. I'm not a biologist, but, the oxygen in the air is critical for various processes in our cells. And then, it's the diaphragm underneath our lungs that causes us to breathe when it sort of changes its shape. Next slide. And we could ask these same questions for galaxies. So we could ask, what are those gases that are flowing into galaxies and out of galaxies? Why do those gases allow the galaxy to grow? How are they related to, the lifetime of the galaxy? And then what is it that causes these gases to change where they are and to flow from place to place? Next slide. So let's start on that first question. So what I have here is a chart. And we're going to build up this chart with different types of gas that are inside of galaxies. And on the left-hand side of this chart, we're going to have really hot gas and gas that's really far separated from other types of gas. And as we go to the right, we're going to get to denser and colder gas over time. Next slide. So the first thing we're going to put in our little menagerie is plasma. So if you've taken chemistry class before, plasma is a gas where the protons and electrons have been broken up from one another. It's what we call ionized. So you have all these charged particles, and you have these magnetic fields that are being generated by flows through here and all this interesting stuff. And to stay in this form, you have to be really, really hot to do that because protons and electrons like to snap together into hydrogen. So anything that's in the form of a plasma is really hot, and generally this is spread out in a large halo around the galaxy. You can have little pockets of plasma all throughout the disk part of the galaxy, but there's a large portion of it around. Next slide. So the next type of gas is atomic hydrogen. So this is what happens when those protons and electrons snap together once they've cooled down a little bit. And this is sort of your classic atom where you have a proton in the center and you have an electron sort of quantum mechanically orbiting around that. And this atomic hydrogen is something that you can find all throughout the disk of the galaxy. And of course, it can also be found further out, but it's much more concentrated in the center than the plasma. Next slide. And sort of the last type of gas that we have is kind of the protagonist of this story. So when atomic hydrogen cools down enough, those hydrogen atoms can stick together with a molecular bond, and they can become molecular hydrogen, sort of like this little barbell of two atoms together. And the thing that's interesting about this type of hydrogen is that it cools down very quickly. Not compared to our lives, but compared to everything else. Once you have a clump of it, it can cool down quickly. And when it cools down, it can condense. Next slide. And so what I'm showing on the left here is sort of one of the most famous images that was taken with the Hubble Space Telescope. It's called the Pillars of Creation. And it's a false color image of giant clouds of molecular hydrogen. Now, what they don't show you in this image is that if you were to look above it, there's a big collection of bright stars that are shining light downwards. And what that light is doing is it's breaking apart the molecular hydrogen. It's blowing it back with sort of this light pressure. But it's having a little bit of trouble. So at the top of these pillars, there are these dense knots of molecular hydrogen that refuse to be sort of so easily destroyed. Eventually they will be, but for the time being, they're in one place. And the reason that they're so dense is because that molecular hydrogen is cooling down and it's condensing and it's cooling down and it's condensing. And sort of in the heart of that cooling and condensing cloud, there are new stars that are forming from this ultra condensed cosmic gas. Next slide. And so one of sort of the big observations in the study of galaxies has shown that these things are very closely related. So if you go and you take a random galaxy and you look at all this molecular hydrogen gas, and then you look at the number of stars that are formed, you find that the more gas there is, the more stars you're forming. And you can look at little parts of a galaxy. You can look at this over and over again. This is often called the Connect Schmitt Law. And what this tells us is that this atomic hydrogen is really the story. So the question is, how do I get more of this stuff around if I want to form more stars? If I stop stars, why do I have less of this than I did before? Next slide. And that at last takes us to sort of the life cycle of a galaxy. So this is a picture that was painted by an expert on the flows of these gases. She's both a scientist and an artist, which is not something I can say. My art is not very good. But it's painting a picture of what the gas is doing around a galaxy. So you have this hot gas that surrounds the galaxy, and over time it cools and it condenses and it flows towards the center of the galaxy because it's no longer hot enough to support itself away from it. And as it flows in, it continues to cool, and eventually it can form these molecular hydrogen clouds, which can then form stars. But the thing is that once you form stars, something interesting happens, which is that those stars start to shine their light out. And some of them might even explode in a supernova or two. And what's happening is now you're shining out all this high energy light. You have these shock waves from supernovae. You have these winds that you are generating within the gas of the galaxy. And you generate fountains of gas that end up getting pushed away from the galaxy. And when this happens, this stops the formation of stars because you've blown out the cool gas that you had in there. And this is the breathing cycle of a galaxy. The gas in the halo condenses, you breathe in, you pull that gas into you. You form stars with it and you blow the gas out, breathe out. And the cycle continues over and over and over again. And this is what we mean for a galaxy to be alive, that it's living through part of this cycle. It's bringing in gas and forming stars. Next slide. But there's sort of another factor in here. There's something a little bit ominous that we haven't talked about, and that's dark matter. So dark matter is one of my favorite topics in all of astronomy. And a talk that explained why scientists currently believe that dark matter exists is its own sort of thing. There's so many interesting stories and facets there. So for now, I'll just start by describing what we currently believe dark matter to be. So the current consensus is that most of the universe, the vast majority of the mass in it, is in the form of a almost perfectly clear, almost perfectly invisible, and almost perfectly collisionless substance known as dark matter. And that this substance has been around since almost a fraction of a second after the beginning of the universe, in the early sort of Big Bang period. It was already there. And that nowadays it's collected itself into massive collections of very dense dark matter called dark matter halos. So what you're seeing here is an image of a dark matter halo that I made from a computer simulation. Now, dark matter is invisible. So to help you kind of see what's going on here, I've colored it so that the regions of space where dark matter is really dense are this bright yellow color, like the center. And then there are certain regions where there's not that much dark matter, those are black. And there's just so much that you can see here. The first thing that might pop out to you is that there's this dense collection of dark matter in the center. It's like this weird, almost circular shape, but once you get further out, it's like a weird potato type thing. Then maybe the next thing that you might see is that there's not one piece of dark matter. There's all these little tiny, smaller little bumps. Those are smaller dark matter halos that are surrounding this. And then, on top of that, this thing is being fed with all these filaments that are coming in that are bringing new dark matter to it. It's got this incredible amount of structure. And then if you look at some of the dark matter halos around it, you might see that there are these streams coming off in every direction. It's an incredibly rich paper, and people have written, or sorry, not a picture, I should say, and people have written thousands of papers about sort of this type of structure. So would you mind pulling up the movie of, it's sort of the red movie, the one that's a link on the internet. So I want to show you a movie of what dark matter looks like as it's forming these halos. So
Can you
it's going to be,
help me find this? Where would I find that?
So this was the this is the one that I sent you in the email.
Oh, okay.
So it won't be a link. It'll right, and
Give me a sec here.
yeah, no worries. So what you're going to see here is it's going to be the same color scheme, and we're going to start out in the early universe. So this will actually be well after the Big Bang had already ended, but before any galaxies or structure had happened. And what's going to start off?
What's the scale here of the image?
Oh, yeah. So sorry, I should back up about that. So the scale here, the way that you should think about this is a really big dark matter halo. So the distance between the Milky Way and our neighbor, the Andromeda Galaxy, would be a pretty small fraction of this image. Okay, great. So here's a movie. So
is there sound? Is there sound on this movie?
No, there's no sound.
Okay.
There's no sound for the movie.
All right. Here we go.
All right, great. So what happens is you have these little tiny perturbations of dark matter in the early universe. We'll talk more about that, but they collapse and they start forming all these little tiny dark matter halos. And you can start to see that web structure forming, but they're in part of a larger sort of overdense region, and they start collapsing inwards. And you can see that these dark matter halos, these little tiny ones, are smashing into one another and forming bigger and bigger ones. And over time, an even bigger dark matter halo is forming over here. And there are these smaller ones orbiting. And if you look at them very carefully, so if you look at these little tiny bright yellow spots, over time, you can see that there are these streams of matter that are coming off of them. They're slowly being destroyed and disintegrated and dissociated, all the dis words there, as this halo is growing. And that's going to become relevant to us down the line. And you can see the structure around this is also forming. So to answer Dave's question from earlier, so the scale of this is quite large. So in this case, we're looking at one of the largest dark matter halos in our simulated universe. So I think the distance between the Milky Way and Andromeda is probably about a tenth of the size of this image. So we're sort of looking at these very large scales. But one of the things that's interesting about dark matter is that dark matter on very large scales and very small scales behaves quite similarly. So if you were to look at the formation of the Milky Way's dark matter halo, it would look very similar to what we're seeing here. Can we go back to the slides, please? Now, the reason that we care about this when we're talking about the deaths of galaxies is that there's a lot of evidence. Next slide, please. There's a lot of evidence that every dark matter halo, or rather every galaxy, is inside of a dark matter halo. And it's very deep in the center of it. So there's this little blue dot at the center of this dark matter halo. And that's the rough size of the galaxy that this thing would be hosting. So they're buried deep inside of it. And that dark matter halo is so massive that it really tells that galaxy where it's going to move, when it gets to grow, and when it's going to stop growing, and if it's going to die, when it dies. It dominates the entire life of that galaxy, which is why we care about the dark matter. Next slide. So let's talk about how these dark matter halos form a little bit. And we'll do this in cartoon version where it's a little bit more clear than the movie, which is just so chaotic. There's so much stuff going on. So in the very early universe, again, a split second after the Big Bang, there was sort of this vast sea of very hot particles. And some regions of that sea of particles were a little bit denser than others. And we call this a perturbation. Which is just a fancy word for like a ripple in this big collection of matter. And what happens is those ripples feel gravity, and eventually they like to collapse back together into a dark matter halo. And so this is sort of what you were seeing in that movie, is that whole image was some very slight increase in the density, and you were watching the process of it collapse. Next slide. And what this means is that really big dark matter halos tend to be separated from one another by very large distances, because you had to have enough room to fit these big sort of ripples that could form each of them. But next slide. It's all sort of ripples on top of ripples. So in between, you can have these smaller objects that form. Next slide. And in between them, you can see even smaller objects from there. And this is sort of what the space looks like, is that you have a couple true giants just sort of roaming around the universe and dominating the local area. And then you see smaller and smaller objects, and you get all the way down to the size of our galaxy, or even much smaller than our galaxy. Next slide. Let's go another one forward too. So now an additional thing about this is that this doesn't all happen at once, and this is something that we saw in the movie. So originally you form something small, and it starts to grow over time. So you have like some little tiny region of that ripple, which is a little bit more dense than everything else, and that's the first thing that forms a dark matter halo. Next slide. And over time, you bring in more and more of that ripple that you were a part of, and you grow more and more as a dark matter halo. And in doing that, you're able to pull in more gas for the galaxy in your center, and that's how your galaxy grows. So that's sort of our broad picture for what it means for galaxies to be alive, and roughly how they're related to dark matter. Next slide. And this takes us to sort of our main goal here, which is figuring out how we actually kill a galaxy. Next slide. So broadly speaking, there's roughly two main categories of galaxies in the universe. There are things that look like the galaxy on the left. So you kind of see this spinning disk that looks really interesting and cool. And it's sort of like everything that you see in these famous images that like the Hubble Space Telescope takes, that people have as their desktop backgrounds, this sort of stuff. But there are a lot of galaxies that look more like something on the right. They're just kind of like a red orb. They're kind of boring. They don't really see anything interesting. Next slide. So this first type of galaxy has a couple properties that are shared. So first, it's blue in its spiral shape, and we'll talk about why that color matters in a second. And it has lots of cold gas inside of it. So sort of those billows that you can see are different types of cold gas. There's this stuff called cosmic dust that's in there that's giving it this interesting shape. There are lots of young stars in there as well. So these bright, shortly lived stars that are popping up all over the place. And in general, they look good. This is the sort of stuff that you show people when you want them to be impressed about astronomy. Next slide. And on the other category, you have galaxies that are kind of reddish. They're oval shaped. They don't have any gas, and what gas they do have is just this hot plasma that's sitting outside of them and not really doing anything interesting. All their stars are kind of old. You don't have any of the exciting young ones sitting around. And qualitatively, I would say that they're a little bit ugly. Now, they're still close to my heart. I love doing analysis on these things, but they don't have quite the same, oomph to them that the other galaxies do. Next slide. So we might wonder, like, how are these things related? Does like one of them turn into the other somehow? Are they totally separate from one another? And the key to thinking about this is those colors. Next slide. So what I'm showing you here is something called a Hertzsprung-Russell diagram. And this is basically a way to think about stars. So on the x-axis, what you're seeing is the color of the stars, with bluer stars being on the left and redder stars being on the right. And on the y-axis, you're seeing brighter stars. Or the brightness of the stars, I should say. And as you go higher up, the stars get brighter. Now, stars can take a lot of forms. And so there's a lot of weird blobs and structure on this. But most stars actually have a pretty simple relation. Next slide. They follow something called the main sequence. So most stars are kind of along one single line that we have here. What happens is, if you're a very massive star, you form on the left side of this line, in the top left corner, which means that you're very hot and you're very bright and you're very blue. And if you're a low mass star, you form on the right. Did I say the right side? The massive stars form on the left side. And if you're a very low mass star, you form on the right side, and you're red and you're cool and you're not very bright. And the thing is that the higher up on this diagram you are, the shorter you live for as a star. You burn through your internal, thermonuclear fuel more quickly the brighter you are and the hotter you are. Just, it sort of turns out that that's the way that the stellar physics works. And what that means is that blue stars tell you something about whether or not you're forming things right now, because you can't have a blue star unless you're actively replenishing them because they die so quickly. And what this means is if you see a blue galaxy, the only place where that blue light is coming from is these new stars that have just been formed. And so that color tells you that anything that's blue is actively forming a lot of stars. Next slide. And so what this tells us is that the galaxies on the left end up becoming the galaxies on the right. So the galaxies on the left are forming a bunch of stars, and then whenever they stop, they turn into the galaxies on the right, where they're not forming things anymore. Maybe there are processes where you could go back, but this is generally sort of the main way that most galaxies are going through their life, is they're doing this type of thing. And the question now becomes, well, how does this happen? Why does this happen? And there's roughly 3 ways. So next slide. So the first is the most gentle way out of all of this. If you're a galaxy, this is kind of how you want it to happen, I would think. And that's just that you grow old. So like we mentioned earlier, the way that a dark matter halo grows is that it depends on sort of the initial configuration of matter around it in the early universe. And it's eventually, gaining access to all that matter and growing and growing. But sometimes you'll just get through all the matter that you're able to accrete, and you can't get any more. And you just slow down and you don't grow anymore. And in this case, what's going to happen is you're going to stop bringing in gas for your galaxy. And that galaxy, it's going to eventually go through its reservoirs of gas. It's going to form more stars and form more stars, and eventually it can't anymore. And at that point, it'll slow down its star formation, and it will die. It will turn into the red galaxy that we saw. And this is known as quenching when it happens, when you are no longer able to form stars. Next slide. Now, another way that this could happen is a lot more exciting. So there's a lot of evidence that almost all large galaxies have a supermassive black hole in the center. And again, black holes are fascinating. You could do a million talks on them. But you should basically think of this as something that's millions or billions of times the mass of the sun, and is this super dense object in the center. And the thing is that in some senses, that black hole in the center of that galaxy is a ticking time bomb for the galaxy. Because that galaxy gets in a lot of trouble if that black hole grows too big. Now, it's not because the black hole will go that it can suck up the entire galaxy or anything like this, but something much more annoying ends up happening from the galaxy's perspective. So as gas falls into the galaxy, some of that gas gets towards the black hole in the center, and the black hole is growing with the galaxy. Now, if you kind of think about what would happen to gas around a galaxy, it's a little complicated, but basically the gas might flow towards the galaxy, and it starts spinning faster and faster, and it gets flattened out into this disk around it. And everything is so high energy. There are all these collisions. You form it in the form of plasma. There are these massive magnetic fields. And sort of decades ago, what researchers at Stanford showed is that if those magnetic fields get caught up in this black hole, you can suddenly release this huge amount of energy that just pushes out all of these magnetic field lines and matter and light in either direction in the form of these massive jets. And that's what you're seeing for this galaxy here. So you can see those little streams going to the left and right out from the center of the galaxy. Those are jets that are formed by that supermassive black hole. And the thing is that if that black hole is big enough, those jets are super energetic, and they can heat up all the surrounding gas so that it can't cool down anymore. And this is a problem, because what happens is anytime gas starts to cool down for this galaxy, once that black hole sort of becomes this really dominant figure in that galaxy's life, a little bit of gas will get onto the black hole and the jets turn on again. And then all the gas stops cooling, all the stars stop forming, and everything's sort of done. And then, the black hole calms down a little bit and the gas starts to flow in. And then as soon as they start forming stars, boom, black hole turns on again and it stops the party again. So once you have that black hole that starts to be dominant, that can be a really big problem for a galaxy, and that can also kill it. Next slide. And sort of the third way that this can happen slowly is just if your dark matter halo gets too big. So what ends up happening is, all this gas that's around the galaxy is in some sense, orbiting the center of this dark matter halo. And the bigger that dark matter halo is, the stronger its gravity is, and the faster things are going to orbit around it. And the temperature of a gas is related to how fast it's moving. And so for these really big dark matter halos, the temperature of all that gas becomes enormous. And it becomes very, very difficult to cool it down. So this is an image right here from a monster of a dark matter halo. It's huge. It has hundreds of Milky Way sized galaxies just careening around inside of it. And it's so big that it's heated up the the gas inside of it so that it's all this super hot plasma that is emitting X-rays in every direction. So, humans can't see X-rays. So in this case, they're colored purple. This is actually an image that was taken by one of my girlfriend's research advisors over at University of Chicago. The gas here is very difficult to cool down, and it's made worse because if you've gotten to this size, you have a really big black hole in the center of your central galaxy here, and so that black hole is not making matters any easier. So these things are sort of working in concert at a certain step. Next slide. But those are sort of the gentle ways that a galaxy can die, some of them more so than others. But there's a little bit of a more exciting way. And this is what we talked about early on with these Magellanic Clouds that were getting ripped apart. And this happens when you're a satellite galaxy. And this is sort of the topic that I study sort of in my day job. So one of the things that we saw in those pictures of dark matter halos and those movies of dark matter halos were these little tiny dark matter halos that were orbiting, and they were getting destroyed over time because the gravity of their central host was ripping them apart. And we also said earlier that most galaxies, or pretty much all galaxies, are embedded inside of a dark matter halo. So if this is happening to dark matter halos, it's also happening to galaxies. So again, the left image is showing a dark matter simulation. You're just seeing the dark matter. And the right image is a different simulation that's showing the stars and galaxies. So there's a big central galaxy in the middle, and there are all these satellite galaxies that are orbiting around it. It's kind of this big swarm of little tiny galaxies. And over time, those things are dying, and they're being shredded apart. Next slide. So this is an image that was taken from a big survey called the Dark Energy Survey. And scientists were using this survey to search for something called stellar streams. And these are sort of the remnants of these galaxies as they get destroyed. They get pulled out into these long, elongated, streams of matter as they do this. This is actually from a paper that my old roommate Nora Schiff wrote. She's currently at MIT. And it's a little bit hard to tell what's going on here. So first, I'll say that most astronomers like to flip the brightness of images so that brighter things are black in the images that we look at, and dimmer things are white, just because it's easier for the human eye to see dark things on white than the opposite. So you can see that there are some lines that are going through here, and those are kind of interesting, but it's a little bit messy. So let's go to the next slide and let's look at some simulations. So this is a simulation of what you would see if your observations weren't so messy and you were looking kind of at a typical, out from a typical Milky Way-like galaxy at their satellites. And you can see all these little dots. Again, the black things are really the brighter things. So these represent satellite galaxies that have a lot of stars in them. And you can see that there's a pattern that shows up pretty commonly, which is that you'll often have some black dot in the center, and then you'll have these two little lines of material that go out in either direction around it. But it's still a little bit hard to see. And the thing is that if we're simulating, there's no reason necessarily that we have to make this something that is exactly what we would see by eye. So let's go to the next slide and let's look at a version of a simulation that's a little bit easier to look at. Now this is pretty cool. So this is a visualization of a similar simulation to the previous one that I showed, where each little dying satellite galaxy is colored another color. Now, obviously, you don't have like pink and purple and green galaxies in real life, so all these are false colors. But this is sort of what the region around a place like the Milky Way looks like. You have all these galaxies that are slowly in the process of being ripped apart. And if you think about it, from the perspective of these little tiny galaxies, our Milky Way is like a horror story. It's a graveyard that's full of all these dead or dying galaxies, and they're just swarmed around it. I mean, it's probably not a fun time as you find yourself falling towards our own galaxy. So let's go to the next slide. So this one is a movie. So if you click on this, that'll take you to a link for this movie, and then you'll have to screen share that new link, I think. And so this is going to be a little bit different from the other images that I've shown. So most of the other images are things that were sort of specifically designed for, to be shown to the general public. This is like a cutting edge research movie. This is something that one of the working groups at Stanford that I'm a part of, we made it a few, I think last week, basically. And what you're going to see,
yeah,
I
Phil,
see it's not shared.
it's asking me
Yeah, let me
for
see if I
access.
can.
If you can
Let me
get
see
that
if I can
shared
do that
real
real
quick.
quickly.
Yep.
All right.
It's funny, it was a little while ago.
Yeah, I think there are two. Okay, am I back now? Great.
Yeah.
Let me know when you get
Yeah,
access,
now
otherwise
I got
can-
it. I got it now.
Wonderful.
Hold on. Stand by.
Great. And I'll let you know when to press play on it.
Okay, I think.
Awesome. Great. So there are two panels here, and we're going to look at the left panel for now. Let's go back to the beginning before we start, because there's a little bit of background we should give on this one.
Yeah, that's.
So ignore the thing on the right. So what you're seeing on the left is the dark matter of a satellite galaxy. And to kind of guide the eye, there's a blue circle showing you where that object is. And then there's a yellow circle that's showing a larger Milky Way sized dark matter halo that this smaller one is falling in towards. And what you're going to see over time is that the dark matter here is going to disrupt, and it's going to form those streams that we saw before. So let's press play and just kind of watch it, and then we'll watch it a second time with some more commentary. All right, so we see it going in, you see that stream forming, it's losing all this matter, and as time goes on, it just gets more and more wound up, and you see more and more complex stuff going on, and it's getting destroyed more and more and more. And that's kind of what ends up happening. And in this case, we're looking at the dark matter, but it's also happening to the stars. Now, the reason that this happens is because of the way that sort of orbits work. So as you get closer to an object, you orbit faster than when you're further away. So if you get pulled off towards the center, you start to outrace the object that you were pulled away from. And if you get pushed away by the tidal forces and all this fun stuff, then you're slower than the object. So we're going to watch this again in 1 second and pay attention to the sort of arm of the stream that's going forward from the center. It's actually been pulled closer to the central object. So let's press play again. All right, right. So right there, you can see that the stuff that's getting pulled closer to the center is the stuff that moves forward relative to it. And so this is what's happening to a lot of these galaxies. So let's tempt fate and try to play the second movie now. So the next slide has another movie that's like this, but it's a little bit different. And so one of the things that we can do is we have satellites, particularly the Gaia satellite, that can take very detailed images of all the stars that are surrounding our Milky Way, kind of the detritus of previous collisions that we've had. And when you look at these, you can piece together the major galaxies that have collided with us over time. Awesome, this is perfect. So in this case, we're going to look at the right-hand panel. And this is showing you the stars. So now we're not looking at the dark matter anymore. And this is much more massive. So in the previous case, it was like this little tiny galaxy that was happy to orbit us. But in this case, it's more like a cataclysmic collision where these stars are coming in and they're in a huge dark matter halo. Instead of having some nice orbit, they smash into one another. And sort of the galaxy ends up getting stuck in the center due to all these really fun dynamical processes. So let's press play here and then we'll pause again in a second. All right, so it comes in. All right, it forms around, you can see a stream and it gets stuck in the center. Can you pause 1 second?
Oops.
Oh yeah, let's go back a couple seconds. Right about there, right. And so it starts, vibrating in the center. It's sending out these shells of stars in both, or shells, I should say, of stars in both directions. And let's press play again. And what we see is as it's doing this, the shells start to deteriorate and eventually you just form this amorphous blob of stars centered near the middle of that dark matter halo, which is where the galaxy would be. And this is actually a simulation of a merger that the Milky Way did experience years ago. For somewhat esoteric reasons, it has a funny name. It's called the Gaia Enceladus sausage. But it's really sort of multiple authors sort of detected this at the same time. And I won't say too much more about that, but that's sort of something that happened to us. And you can see signatures of this exact event in the stars around our Milky Way. And it's pretty cool. Next, let's go back to the slides and then go to the next slide. So to close out, we're going to talk about some really cutting edge stuff. So this is sort of a descriptive picture of what it's like for these. But the thing that's cool is that you can leverage these dead galaxies to learn more physics. So here's my, a really bad cartoon that I made to try to illustrate this. So one of the things that you can do is if you change how your dark matter halo looks and is shaped and all of these sorts of things, you can change the shapes that those stellar streams take on. So, if you make your dark matter halo denser or rounder or more oblong, those things will splay out in different directions and their orbits will look different from one another. So you can go and you can take a census of what these objects are doing, and you can back out information about the dark matter halo that we're in, despite the fact that you can't see the dark matter. You can tell how it behaves by the impact that its gravity has on these stars. And this is one of the big projects that people use stellar streams for, is to try to back out information about our dark matter halo and how it looks. Next slide. But maybe even more fundamentally than that, we can probe the nature of dark matter itself. So the way that I like to think about it when it comes to dark matter is that scientists today are in a pretty similar spot to the way that, say, an ancient Greek or a medieval Malian scientist was when we would think about water. So they knew a lot about water at the time. They knew all sorts of properties that it had. They knew how it moved, how it behaved. They knew how it interacted with other matter, but they didn't know that it was made up of 2 hydrogens and an oxygen. And because of that, there was a lot of stuff that they couldn't know about water. Even though they had all this empirical information, they knew all these things about it. And that's a similar state to where we are with dark matter today. So we know a lot about it. We know that it's in dark matter halos, and we know a lot about how those dark matter halos work. But we don't know, is it a specific type of particle that we've never seen before in our accelerators? And if it is, what type is it? So one of the major theoretical projects in astronomy right now is trying to see how the properties of dark matter could affect the real world if you change them a little bit. What I'm showing here is a plot that shows 2 different types of dark matter from a simulation. So the x-axis here is the distance from the center of the dark matter halo in the simulation. And the y-axis is the density of that dark matter, how much of it there is. And so these curves are going from the top right down to the bottom, the top left down to the bottom right, which means that, as you go out in the dark matter halo, it gets less dense. And as you come back towards the center, it gets more dense. And the 2 different curves here are 2 different models of dark matter. So the black curve is kind of like normal dark matter. So it's the most boring dark matter that you can sort of think of. It's the dark matter that we usually use in our theoretical models when we do stuff. And what happens is you just keep getting denser and denser and denser and denser as you get closer to the center. And you end up looking sort of like this cartoon on the right. And here I've colored it darker and darker as you get closer to the center. And there's sort of this really dense inner region. People call it a cusp for these sorts of dark matter models. But the blue curve is showing another version. And in this, what you do is you say, well, I think for the most part, it's mostly boring. But sometimes that's not true. Sometimes it can collide with itself or collide with other matter. And what happens when you do this is you flatten out that inner density, you make it less dense. And you end up looking like this cartoon on the left, where you don't have that really dense inner region. And this can sort of modify other things too. So next plot, please. So what I'm showing here is sort of a simulation of 2 different dark matter models for sort of, I think this is a Milky Way-like galaxy, the dark matter around it. And we've been running similar simulations over at Stanford, but sort of those things haven't been finished yet. So I'm sort of showing another group's work on this. And so the leftmost plot is showing you a normal, dark matter halo with normal dark matter. And the right, and the plot in the middle is showing you one where they've made the dark matter interact with itself. And you can see that a couple things have happened here. So the thing that probably stands out the most is that it's rounder. So you don't have this oblong shape to it. Another thing, and this is a little bit harder to see, is that the halo on the left is denser in the center than the halo on the right is. And then, excuse me, another thing, and this may be the least obvious of all, is that there are fewer little tiny dark matter halos orbiting this one. And that's because when you lower that density, you become less durable, and it's easier to get destroyed, and it's easier to die as a galaxy if you're in some form like that. And the thing is that all three of those things are things that we can test empirically. We can go and we can count the number of satellites that are out there. We can go and we can look at how fast those stars are moving, and we can figure out information about how big those dark matter halos that are hosting them must be. We can go and we can use these stellar streams to figure out, what the shape of the dark matter halo is. We can use stellar streams or any number of other measurements to try to figure out how dense the center of our dark matter halo is and how much matter is there. And actually with that, that's enough to rule out that center model. So just using these observations of dying galaxies, we were able to say that this center model cannot be true. We know things about dark matter, which is that it doesn't work like this. We don't know how it works, but it's not that. Can we go to the next slide, please? Great. So what ends up happening is when you decide that you're going to create a new dark matter model, you have to kind of make it fit into this space where it's still consistent with these observations that we have. So this plot on the right is showing another dark matter halo, and this one does interact, but not as much as the central one. And because of that, there are little changes. They're subtle. Some of them you can see by eye if you squint really closely, but you can't see all of them. And you have to kind of do this statistically. You have to look at large samples of things. And the hope is that as we build larger and larger samples, we'll be able to rule out more models more sensitively, or hopefully, and this is always the dream, that we'll be able to say definitively that we're in a case like the right and not a case like the left. And one of the main tools that we would use to do that are these galaxies that are dying. And really, this is one of my favorite things about studying astronomy in general, which is that you have these incredible objects, these things that are almost incomprehensibly massive. They take these incredible timescales to do anything, but it's still possible to use them to unlock physics and to try to understand our universe better. And that's sort of my favorite thing about studying how galaxies die. So next slide. So on that note, that's sort of my talk. I'd be happy to take any questions. I'll do my best to answer them. And if you sort of stump me, I'd be happy to sort of follow up and look up more information for you later.
All right. Well, let's get Dave back here. Hey, Dave.
I'm here.
Well, why don't we start with you? And I know you've always got good questions. You tend to save them up. And then we'll start fielding questions from our audience.
So Phil, I'm going to ask the obvious question,
Great.
Which is obvious. Well, the question is, we know that dark matter has mass. We know it doesn't interact very much with its surroundings, which strongly suggests it's non-baryonic, which means either it's part of our model for our general the standard model for particle physics, or it's not. The one candidate that sticks out in the standard model, I think, is neutrinos. And
right.
The question is, but I think there are some problems with neutrinos, and I'd like you to explain that, and I'd like you to explain whether there's anything else in the standard model that could possibly be a candidate for dark matter.
Great. Yeah, I would love to answer that. So first off, I'd like to back up and it's such a good question that I have to explain things even about the question itself. So one of the big observations that we have about dark matter, which is a little bit weird, is that if you have two giant clumps of dark matter that are traveling towards one another, they can pass right through like they were ghosts. And this is not something that happens with normal matter. So if you have a big cloud of gas and another big cloud of gas, they feel pressure and friction when they smash into one another. And so there are numerous observations that we have that show cases where either individual dark matter objects have passed right through one another with no impact, or cases where if you look sort of statistically at the distribution of matter in the universe, they could only find themselves in that configuration if there were no collisions. And so what this tells us is that whatever the dark matter is, it can't be something which collides very easily. Now, maybe it could collide a little bit, but the whole picture doesn't work unless it's nearly collisionless. And so the first thing that you would want to do is you'd want to say, well, we know about a lot of particles out there. Could any of them be it? And so there's one candidate which is sort of the obvious first thing that you would check, and that's something called a neutrino. As a little bit of history, sort of back in the early days of particle physics, people would look at neutrons, so one of the core particles in a nucleus, and they would leave it alone for a while, and eventually it splits off into a proton and an electron, and they go off in other directions. And what people realized after a while is that things weren't adding up. So without getting sort of too technical, the inputs weren't matching the outputs. There was a little bit of extra, something called momentum, that wasn't being accounted for. And what people eventually realized was that there was a little tiny particle that was very difficult to detect, called a neutrino, that was also being emitted. And neutrinos are very, they don't like to collide. They can travel through the body of the Earth and come out the other side and hit a detector on the far side of there. They're pretty incredible. And in fact, when we build neutrino detectors, we'll often beam them through the Earth from the facility that makes them to a facility, somewhere else in Europe that can detect them. So they seem like a pretty good candidate for this. But there's an issue with sort of normal neutrinos. So the things that we know and love, and that's that they move very, very fast. So, in this picture that we have about dark matter, what happens is you have this, ripple where it's a little bit more dense than everything else around it. And early on in the universe, you get pulled towards this, and that's how you eventually form the dark matter halo. But that only works if the dark matter isn't moving fast, if it's something called cold dark matter. Because what happens is otherwise those neutrinos have too much energy to be bound to that particular perturbation of mass. So it's sort of like, if you have a rocket that's going at a certain speed, it can orbit the Earth, but if it's going really fast, it just leaves the Earth and it never comes back. And that's sort of the case for neutrinos. So neutrinos would be something called hot dark matter. And for a while, people were entertaining different ideas related to hot dark matter. But in detail, when you run those simulations, you end up finding out that they don't look like the real universe. And the thing that's different is that they don't form enough dark matter halos to populate the universe that we see. So that's why we think it wouldn't be neutrinos. And I don't think that there are any standard model particles that are sort of good substitutes for dark matter. I don't think there's anything that would quite match it. So in order for dark matter to be a fundamental particle, it would need to be something new. Now, people have suggested that maybe it doesn't have to be a standard model particle. Originally, back when the first measurements were made, some people suggested that it could be, a bunch of planets that we didn't know about or something like this, black holes, this type of thing. And there are various observations you can do that make that sort of intrinsically unlikely. But I think the most fundamental one is that there's evidence that dark matter was around early in the universe, before the first stars formed. So if they are something that isn't just a random particle, or some collection of like 20 particles that we don't know about or something like that, they would still have to be exotic. They would have to be like black holes that were formed in the early universe or something like that. So either way, it's something pretty weird, and it's something that no one was asking for before they ended up making these measurements. Does that answer your question?
Yes, it does. And this strongly suggests, I think, that that, as you said, dark matter is made of something exotic that we don't understand, which means every time we actually study something like this and then we figure it out, it changes the way we see the universe, the way we see physics, the way we see the standard model. There's a major breakthrough. Again, our whole species is going to have an epiphany when we finally understand what dark matter is.
I hope so. You know, if it does turn out to be black holes or something, I would have loved that if that turned out to be true. That would probably be the least exciting thing. But you know, certainly the second that we find out what dark matter is, the amount of funding for this field of study is going to go through the roof. But I think second only to if the people who study planets around other stars find aliens. I think that would be the thing that really gets people excited more than anything. But that's the dream that a lot of people have, is that they're going to, you know, find the concrete evidence for one form of dark matter, that they're going to help for that. That's one of the major projects for exactly the reason that you said, which is that it'll totally sort of change this model of physics that's been one of the most successful theories of scientific theories sort of ever. Something called the standard model of particle physics, which is, you know, the properties and connections between all these different particles that we see in the universe.
Yeah, I remember the time before we had the standard model when there was this massive confusion in the mid 60s about what was going on, and it was an amazing time with all the resonance particles and everything else. I'm going to shut up. I assume we have.
No, that's okay. It's interesting. I'm going to editorialize Rich and Sue's question, because they were talking about M81 and M82 and proximity pass-through physics, and I was thinking along similar lines, but about the stories that were coming out over the last week or two about the formation of ring galaxies, how some of the models of ring galaxy formation have come to fruition. And I'm wondering to what extent you model galactic collisions as part of this research, and does it offer any insight to the nature of dark matter? And does dark matter play a role in those collisions?
Yeah, so galaxy collisions are an amazing subject. They are so cool. And in fact, that is a major sort of thing that some of the research groups at Stanford are looking into, and that I'm sort of working on a lot. So the simulations that we were showing with those movies are specifically made to look at what happens in the aftermath of a collision between galaxies. You know, in our specific case, we're looking at our Milky Way. So when a galaxy collided with us, what happens to our galaxy? And what does the detritus look like afterwards? How can we piece out more information about this? And what can we tell about the history of our own galaxy from this? But there's plenty of studies that look at other things too. You know, there's plenty of, you know, more statistical looks, like on large scales. If you look at these distant galaxies, that you can see what happens. If you look at, so I think you mentioned M81 and M82. So those are two relatively nearby galaxies, if I'm remembering my galaxies correctly, that are quite close to one another. And they have some interesting properties in their satellites as well. Yeah, so satellite, you know, galaxy collisions are really interesting. And, you know, at the risk of sort of getting myself in trouble by talking about a subject that I'm not an expert on, even so the consensus in amongst most astronomers is that dark matter exists. There are some holdouts who don't believe this and think that maybe you can do this by modifying physics. I personally don't believe this, and I think there are some problems with this theory, but there are many very good scientists who do believe this. And just the other day, this group put out a simulation where they, you know, collided two galaxies together, where they had modified the physics in this way with no dark matter, and we're looking at the results of that. And there's lots of interesting things there. Again, I don't think that it really supports the idea that, you know, you can modify gravity and physics in this way, but there's some really interesting work, even if you aren't looking at it in the context of dark matter. There's so many cool things. So it's a rich topic. There's so much information there. And it's a critical part of sort of the way that we understand these things.
Bruce asks, since dark matter feels gravity, feels in quotes here, but is not visible, wouldn't it condense into something like a black hole, which would distort more distant light sources? Therefore, couldn't we see dark matter as some sort of distorting gravitational lens?
Love that question. That's really, really good. So, you know, the question is basically like, something's got to give at some point. You can't just keep on collapsing forever. At some point, you either need to collapse into a black hole, or something needs to stop you from collapsing. And, you know, so in the case of normal matter, something that can stop you is pressure. You know, you have gas that comes in and it feels the denser gas underneath it, and that pushes you know, a force outwards that stops you from collapsing. So this is what holds our sun up. That's why our sun doesn't collapse into a black hole. because there's pressure holding it up. But there's something else that can hold you up. And I'm going to use the sort of technical physics term. It's something called angular momentum. So our galaxy doesn't collapse in on itself. But our galaxy isn't actually held up by pressure. So our galaxy is mostly a bunch of stars that are just sort of rotating together. And the reason is that if the more that you're spinning, the harder it is for you to get close to the center of an object. How about this as an analogy? So this is kind of a fun thing that you'll do sometimes in an intro physics class. You'll put someone in like in an office chair, and you put like two little 1-pound weights in their hands, and then you spin the office chair, and then you try to pull your arms in. And so what happens is, as you pull your arms in, you start spinning really, really fast. But it's also really hard to push your arms in. It's hard to move those weights closer together because of this idea of something called angular momentum. It makes it harder to do this. And so what ends up happening is you have these dark matter halos that are collapsing, and they're formed from some sort of large, again, perturbation in the early universe. And that thing is spinning a little bit. And it's spinning because, it's getting tugged on by other, ripples in the dark matter field. And as it's collapsing, first it starts off with its arms far out like this. And then as it gets smaller and smaller, it starts spinning faster and faster and faster. And eventually that little tiny bit of angular momentum that this stuff had at the beginning is enough to keep it from collapsing inwards. So you're right that things would happen there. Now, the case where you could get yourself in trouble is if this stuff could cool down. So if dark matter could collide, you might have it in some equilibrium state, but then it could collide more and more and more and more, and it could get denser and denser and denser. And so one of the things that's actually a constraint on dark matter models, I don't think it's the most competitive constraint, but it is a constraint, is that you need to not form a bunch of black holes, because then you would be able to observe it. So if you have really aggressive cooling that can kick in sort of one regime, and you would start forming these types of objects, you need to make sure that it's not so aggressive that it ends up, forming black holes that we should have seen but don't. So that's a great question, but it comes down to the physics of how spinning things work. That's why they don't collapse into a black hole.
All right, question from Ethan. I understand that dark matter is what keeps the outer stars in spiral galaxies moving at the same speed as the innermost stars. But if that's the case, and at a smaller scale, why don't the outer planets in our solar system move at the same rate as the inner planets? Is it because
beautiful.
There's not enough dark matter in our solar system?
So first off, yes. Full stop. Great. All the conclusions that you had there were perfect, and it's completely correct. But let's back up and talk about this a little bit. So first off, I'll say that sort of the current theory for the dynamics of the solar system is that the main thing that's important for how fast planets are orbiting is just the sun. So we don't think that there's any significant amount of, there is dark matter near the solar system, but it's not in a large enough amount to be something that would change how the planets are orbiting. And like you were saying, Ethan, the planets that are closest to the sun are just whipping around. Like Mercury is really fast and Pluto is really slow. And this is a property of gravity. So if you're orbiting an object, you should get slower as you're further away from it. But there's another property, which is the bigger the object that you're orbiting, the faster you should orbit. And so what happens with a galaxy is, when you're in the galaxy, let's say that you're like sort of halfway along the disk of this galaxy, and you're sort of rotating at another speed, at a certain speed, based off of your distance from the center and how many stars are inside of your orbit. If you go and you then look at a galaxy, at a star that's twice as far out, two things have happened. So one is it's gotten further away from the center, and then the other is that you've enclosed more mass in your orbit. And it just so turns out that for galaxies, these things basically cancel out. So as you go further out from the galaxy, your speed does not decrease. And it's possible for this to happen without dark matter. So people sort of knew that galaxies within the galaxy disk rotated like this. And that didn't make them think that it was dark matter. They sort of knew this in the early 1900s. The thing that was weird was what happens if you look at, say, a star or a cloud of gas that's far from the edge of the galaxy. Well, what you would predict is once you've gotten beyond the edge of the visible galaxy, then you're just like the planets in our solar system. You're getting further away, but you're not enclosing any more mass. So your velocity should go down. You should spin slower like Pluto. But when people measure this, and the big famous measurement, the best one on this was by Vera Rubin and Kent Ford in the, I think 1978. Maybe I'm getting the date wrong. But they sort of had this amazing spectrograph. It was sort of the best in the world at the time, and could take measurements very, very quickly. And they were able to measure these clouds that no one else had really been able to measure at a greater scale and further away from our neighboring galaxy Andromeda. And they saw that the velocities didn't go down. And what that meant is one of two things had to happen. Either gravity and physics had to work different, or you needed additional matter between the edge of the galaxy and where you were seeing. And so the answer that people eventually sort of took as the consensus view is that it was dark matter, as opposed to sort of changes in physics and gravity. But you're totally right about your conclusion, which is that the thing that we can conclude from this is that there is not a lot of dark matter in the solar system, specifically because it's not flattening the rotation and making everything rotate at the same speed.
Right. Bill asked a question. This is a vast question. I don't know how to answer this in a couple of minutes. How does one calculate the percentage of mass dark matter makes up in the universe?
Oh, I love this question. This is so good. And the answer is it's really hard. So after people found dark matter, they didn't know what fraction of it was sort of normal matter versus not normal matter. So they knew that it was there. But the thing is that, like, you can't measure out into the outskirts of a dark matter halo. So you can kind of do it in the center. So you can go and you can look at how fast these stars are orbiting near the center of the galaxy. And you can say, okay, this is how much I would expect from normal matter. Excuse me. And it's orbiting this much faster. So I can kind of do the math and I can say this much mass is there. But eventually you run out of stars and gas clouds that you can do this for. And there's just this vast expanse outside of that. And you don't know how much dark matter is there. You can run a simulation that'll tell you, but maybe your simulation is wrong. Like you had to come up with what that model was. So I think fundamentally there are two measurements that are really the key for this. So the first one is a little, I mean, neither of them is very intuitive. I'm going to do my best, and I'm going to apologize if this is not super clear. But the first is for very large dark matter halos. So these galaxy clusters. So these are the things where you have like 100 or 1,000 Milky Way sized galaxies that are just orbiting a center and getting totally obliterated by the tidal forces. So what happens there is that you have a lot of hot plasma, and what you can do from this is you can see most of the non-dark matter that's there. You can sort of add it all up, and you can see the stuff that's in the galaxies. You know how much a star weighs, and you can figure it out from that. And then you have this plasma, and we know enough about plasma that, if we see light from a certain type of plasma, we know how much of it is, what temperature it's at, and what pressures it's at. And from that, you can figure out how much normal matter is there. And then you can kind of do this thing where you look at the temperature of the plasma in different places. You can figure out how much dark matter is in the galaxy cluster. And so that can give you one answer. And I think that was the first sort of evidence that people were using for the ratio between dark matter and normal matter. But there's a second way, and that's to go to the early universe. And so I'm trying to think about the right way to do this. And I'll say that if you want to look up what I'm about to say more technically, the term of art is very scary, but the thing that you would Google is something called Baryon acoustic oscillations, which just means baryon sound waves, which just means sound waves through normal matter. It's a big complicated word, but basically what happens in the early universe is that the early universe is really hot. And so what happens is if you have some fluctuation that has both dark matter and normal matter in it, that normal matter feels an immense amount of pressure, both from itself and all the heat and from all the light that's being shined in every direction by these ultra hot atoms. And what this happens is it causes that normal matter to want to flatten out and equalize. So, there will be some really high pressure region in the center of that ripple, and it tries to flatten out into being something that's not like that. But the dark matter halo does not care about pressure, and it does not care about light. The dark matter in the sort of little density ripple doesn't care, and it just stays as is. It doesn't do anything. So once the universe cools down after the Big Bang is over, you have dark matter and normal matter that are distributed differently from one another. And they kind of get into a tug of war. So the dark matter is trying to pull the normal matter back towards the center. And the normal matter is like, no, can you come out here? And so you can look at who wins that tug of war to figure out how much dark matter versus normal matter there is. And it's a very precise measurement. When you sort of look at the signatures of these things, you can work it out from that. It ends up getting quite technical. And there's certain steps in that calculation that are still kind of a mystery to me. They're a little bit complicated, but that's the general idea. So one of them is by looking at very massive collections of galaxies, and the other is by doing statistical analysis of things that would have happened in the early universe and their impact on the current universe today.
Phil, those two numbers roughly agree with each other?
Yeah, they roughly agree with one another.
Okay.
I think that the first number is less reliable, so there's sort of big error bars on it, but it is generally consistent with the other number.
Okay.
Can you tell us more about the computer language and hardware that's used for these simulations?
I would love to. So there's multiple different. So first off, astronomy is a very computer-based subject these days. So when I was getting trained, there was a heavy focus on pen and paper math, which is sort of what physicists have been doing for sort of years, and less of an emphasis on programming. But I ended up, taking computer science along with that, and ended up sort of doing a lot of programming. And what ends up happening is that most astronomers end up using a programming language called Python. So this is a programming language that makes sort of life easy for you. There's a lot of tasks that feel like they should be simple to do that are complicated to do in other programming languages, but are not complicated in Python. And it's particularly, convenient to do certain types of analysis. Now, the trade-off is that Python is slow as heck, and it is not a fast language. So if you're sort of running it, things can take a while. But there's certain tools that people have built that make it so that you don't pay too high of a price for this. For those in the know, it's something called NumPy and SciPy are sort of the names of the game here. Then there's sort of a smaller group of people, and these are the people who write like the simulation code or like the really hardcore analysis code. And they generally do things in C, C++, Fortran, the classic things. I'm kind of a weirdo. I use something called Go, but we don't need to talk about that too much. But there's a wide range of languages, but basically a lot of people use something called scripting languages, and then others use these faster, low-level systems programming languages to do things.
Great, thank you. Dave, do you have anything else? Because I'm going to give you the last word if you'd like.
I can't think of anything right now. I'm still stunned by all of this.
I know it was a very unifying talk about a lot of different topics.
Yeah.
That we've often had lectures about, slices of this, but this really put together a whole bunch of different topics all at once, and it's a lot to take in.
On the chat from Marianne, did you see that just now? She said,
did she finally? Oh, she.
But cannot ask.
She goes, I have an idea about dark matter, but cannot ask about it because I would just be laughed at.
Well, I would never.
Come on, Marianne. When do we ever laugh at you?
That's what I'm here for.
Yeah, that's right. That's why we have Dave. All right. Well, I'll tell you what, Marianne. You could forward me your idea, and I'll send it off to Philip.
I'd be happy to answer.
Phil, thank you. I have to say that one of the exciting things about having these meetings and being a program director is that we get to meet these really outstanding, brilliant people. And it makes us proud of our species, that we're sort of members of the same species as this really smart person who can do this really neat stuff. And it's cutting edge, that helps answer some of the most profound questions that our species has had ever since a primate looked up at the sky and wondered, what the heck is that all up there? So Phil, thank you very much for participating in this great task and helping us understand more about this. And I'm still just absolutely amazed that that dark matter is something that it doesn't fit in the standard model near as we can tell, and that when we figure this out, and I hope I'm alive when we do, that it's going to really just change the way we see the universe. Phil, thank you very much for a wonderful talk.
Thank you so
Yeah.
much for the kind words, and thank you for having me.
All right, thanks everyone, and we'll see you next time.
Oh, wait.
Oh,
I have
what
to
you got?
Okay, speaking of really neat stuff, next month's speaker is Dr. Ruslan Belikov of NASA Ames, and he is working on direct imaging of extrasolar planets. And if you don't think that's exciting, you don't have a pulse. So thank you very much.
It's so cool. So much cool work is being done
That's
there.
May 21st. So Phil, you're invited. You can ask a question.
All right, take care, everyone.
Great.
Good night.
Thank you. Have a good day.
Good
Yeah.
night.